Hello, good morning, everybody. Uh, First of all, I would like to make an announcement regarding our first midterm. It's going to be about 2 weeks from now, March 10th on a Wednesday. It will be online, be available on Blackboard. So the midterm will be available for 24 hours, and you can choose to do it in any 2-hour period. It will cover chapter 1 and 2, that's the content. Will be 3 short questions and 3 longer questions. There is a practice exam with similar format along with the solutions that's already up on Blackboard, so you can use that as a practice. You can use all your notes and books, but do not collaborate. Work on your own, so that's the policy. I will continue to put reminders next week, just to remind you that the midterm is coming up, and send an announcement on Blackboard, okay? Are there any questions?
Professor, I have a question. So some of the problems on the homework requires Mathematica. For the midterm, is Mathematica allowed?
They will not be needed because if there is a integral that cannot be solved, I will not ask you to do such an integral. So that kind of problem will not occur. But yes, but in terms of if you want to use Mathematica to help you evaluate integral, that is totally okay.
Okay, sound good. Thank
Yeah.
you.
Mm-hmm. Thank you. Any other questions? Okay. Okay, today we are discussing a topic of conductors, and hopefully we will be able to review quickly a couple questions on capacitors. So let me ask you guys this question. What do you think a conductor is? What is a conductor?
Conductor is when electrons are free to move. Specifically, electrons go to the surface of whatever shape you got.
Yeah, conductors is when they're free charges, the electrons are free to move. We have an unlimited supply of free charges in conductors. So for a perfect conductor, then the perfect conductor contains an unlimited supply of free charges. And the charges are free to move. In real life, the metals, they are really good approximations for perfect conductors. Capacitors are made of conductors, right? They are two pieces of conductors separated by a dielectric. For example, if you put two metal plates separated by a distance, so you have air in between, and that's a parallel plate capacitor. But first of all, let's think about look at some of the features of conductors. There are many interesting features. When you put the charges in or out of a conductor, what will happen? Think about the feature for conductor. Next couple of clicker questions really relies on the charges are free to move inside a conductor. So I want to remind you of that when you answer these questions. First question, we put a point charge outside of a neutral conducting copper sphere. So this is a conductor. It's neutral. And you put a point charge outside of that. What is the E field at the center of the sphere? Okay. I'll let you guys vote. Maybe you will not really need much time at all to know what the answer is, but when you discuss, maybe focus on formulating a reason why that is, and how could you be able to convince people why that is, because I know a lot of you may already know the answer. Okay, so maybe a minute on this question.
Professor, I'm really sorry, but can I get assigned to a breakout room?
Yes, yes.
All right, thank you.
Okay, any last minute votes? Okay, I'm going to go ahead and end this. Let's take a look at your vote. Okay. All right, so anybody would like to tell us, majority voted for D, although we shouldn't always be discouraged if your vote is not the same as a majority. Sometimes a majority voted wrong. So in this case, anybody would like to tell us how do they know what the E field is inside at the center of this metal sphere?
When there's a charge outside, there's an E field inside the conductor. It'll the charges will move to counterbalance that field and reach equilibrium.
Okay, very good. So important thing, this is an equilibrium situation, which means that if the charge were moving, they have already moved to the proper place. So the thing is, what you're just describing how come the E field is zero, right? How do you achieve that zero? Wouldn't there be an E field at the point of the center due to this point charge outside? The idea is because they will be the copper plate will be polarized, so that the polarized charges will produce an induced E field to cancel the E field due to this point charge, giving you zero E field in the center. That's sort of a process of how to achieve that. But there's another way to always know that E field is always 0 inside a conductor, because precisely due to the definition, remember we said the definition for a conductor is the charges are free to move. So if the E field inside the center is not 0, then the charges are not going to stop moving. These electrons inside the conductor are going to continue to move. It only will reach a equilibrium situation, static equilibrium, when the E field is 0. Otherwise, it's going to feel this E field is going to move. It's going to move to a place it's going to redistribute themselves so that the E field is 0. So you can use that argument to know that whatever situation you're given, the E field inside the conducting material will always be 0. Okay, so and how the charge is achieving that, if you want to know the process, is the cancellation of the induced field cancels this point charge. The answer is 0. Very good. Now I'm going to give you another situation. The copper sphere used to be neutral, but now I'm putting a total amount of net charge Q on it. So when we say it carries a total amount of charge positive Q, these are net charges, because we know any material is made of a lot of protons, electrons. They always have a lot of positive charges, a lot of negative charges. So when it has a net Q, meaning the total amount of positive charges doesn't cancel out the total amount of negative charges with the total amount of net positive Q exists on the sphere. So when we're drawing the charges, we usually only draw the net. We don't draw all the positive and negatives, because if it's neutral, then they all cancel out. Then we don't draw any charges. Okay. So now we give the copper sphere a net charge. What do you think the E field is at the center? Okay. Again, you like to again discuss, I will give you a 1 minute. Okay, so open up breakout rooms. Take a screenshot before you go.
Professor, I was in room 9, but my audio cut out again, so I had to leave and come back. Sorry.
Okay, Chelsea, right?
Yes.
Okay, I'm gonna put you in.
Thank you.
Sure.
Dr. Brain, I also need a room. I
Me
got
too?
here a few minutes late, yeah.
Okay.
Me as well. Oh,
Thank you.
Okay. Okay, let's take a look. So actually less people voted for E equal to 0 now. Probably because I've added the positive charge on the conductor. But would you argue that if it's still a conducting material, if the E field is not 0 in the center, it's not going to reach a static equilibrium, which is what the problem is talking about. We're talking about static equilibrium. Actually, the charges may get redistributed very quickly. So when we are talking about a situation where we want to evaluate what's going on this conductor, we're always looking at a static equilibrium. Because the moment when charges get polarized is so quick. Okay, so remember what I said previously, if you're dealing with conducting material, then the E field is always 0 inside the conducting material. The charges will move to whatever situation it requires, it needed in order for you to have a 0 E field. Okay, so don't be thrown off by the extra charge. You're still dealing with the conducting material, so you're still dealing with the same 0 E field inside. So my argument for conducting material is such that E is always 0 inside conductors. And why that is? Because if E is not 0, then the free to move charges will feel this force, and the charges will continue to move and redistribute until the E is 0 inside, and then they reach static equilibrium situation. Okay, and there's another thing, there's some interesting facts we can get for conductors is, okay, we just established E has to be 0. What about charge density? So rho over epsilon naught is divergence of E. So this is Gauss's law, right? So rho is also going to be 0. Charge density is 0. So inside conductors, okay? Now this seems a little strange because of course all the materials are made of positive proton and negative electrons. Why do we see the density is 0? So density is an overall situation. If it overall appears to be neutral, then you can say the charge density is 0 because the positive charge and negative charge, they cancel each other. So rho is always 0 inside the conductors. That means if you have extra or net charge, excess amount of charges, then these extra charges will live outside. They're not going to live inside the conductor. So the excess charges will move to live on the surface of a conductor. So that's something else that we found out about the feature of a conductor. There's something else that let's look at the potential. The potential difference between any 2 points on a conductor is defined to be the integral negative from A to B E dot into dl. Now, if E is 0 inside a conductor, then this potential difference will be 0, which means point A and point B have the same potential, right? So that's why we also know for conductors are equipotential objects. So any point on the conductor has the same potential throughout. So if you have a conductor that's shaped like this shape, then the equipotential lines are parallel to the surface. If your conductor is sort of this round shape, then the equipotential lines are also the round shape around the surface. Okay. The conductor surface are equipotential surfaces throughout the surface of the conductor. This is all derived from E equals 0 of the conductor. There's something else we can do. If the conducting surface is equipotential and we know the E field is perpendicular to the direction to the equipotential lines, right? E is a gradient of V. So E points in the direction where V has the biggest change or fastest drop, so that E will be perpendicular to the surface, because equipotential are the same shape as your surface, and E is perpendicular to your potential line, so E is perpendicular to your surface. And that means if you have a non-zero E field, the E field can only be a perpendicular on the surface of conductor. You should not have an E parallel on the surface of the conductor. And why not the parallel? Because, well, if you have a conductor, right? This is a conductor. And if you have an E field that is parallel to the surface, then that means your charges are still moving, right? If you have charges here, negative charge, if you have a parallel, it's going to flow along the surface of conductor, then you're not at equilibrium. It's not going to be a static situation. So you can only have E field perpendicular to the surface this way, right? So I think if you recall the experiment you mapped out in 1520 or 133, where we had different electrodes, we made conductors and we tried to draw the equipotential lines. I don't know if you still remember, and the E field is always perpendicular to the shape of the conductor that you're given. Okay, and there's only a parallel, perpendicular component, not the parallel component. You can see all of these are simply derived based on the pure definition of what a conductor is. Although these I can derive it later from Gauss's law, but we will look at that later. Okay, so just a couple quicker questions, really trying to get the idea. E is 0 inside conductors, and don't be confused by some extra information. Now, conducting surface is going to give us some interesting results. So for example, we have a large copper plate with uniform charge density sigma. And imagine we draw the Gaussian surface like this. So now we have Don Gauss's law to calculate the E field near a uniform large sheet. Now it used to be that large sheet was not a conductor. We were doing a insulator situation before, but now it's a conductor. We have surface density sigma. So use Gauss's law to calculate the E near the surface. What do you think that is? And you probably could guess that the answer might not be the similar as before, because if it is similar, why do we ask you to do it again? Now, if it's different, how is it different? And again, I would ask you to think carefully again. What do we just emphasize over and over again about the E field inside the conductor? That's going to be very important in answering this question. So I'm going to go ahead and let you discuss this question for a couple minutes, okay? And you can take a screenshot before you leave. Okay, I get everybody's answer. So let's take a look at our results. Kind of pretty much split between A and B. Okay. All right. I'm gonna go through the derivation of Gauss's law and let's work it out together. So I'm showing you a drawing of a conductor, and here we have this. This is the surface. I'm going to draw a Gaussian pillbox with tiny height h, and with a surface area a. Now, we have established that E field is not going to be parallel to the surface. So whether we choose a tiny height or not is kind of relevant, but this is a common technique that if you choose your height to be very small, you can neglect the possible contributions of the flux through the side of the side surface. So you only need to consider the top and bottom surface. So the pillbox has top and bottom surface of A, and let's look at how the Gauss's law going to work out. So E dot into dA equals Q enclosed over epsilon naught. Okay, so E dot into dA, if we have positive charges on the surface, then the E field is going to be pointing away. So I will have, so the flux here on the top surface is E, right above the surface, outside, times this total area A. Now the side we don't have to consider for the reason that we know there is no parallel component E, or because we have treated to have a very tiny height of H. Then we have E inside times the same area A. Now the inside would be the E field on the bottom that's going through the bottom surface. So what is the E field right at the bottom surface? So what is E here? I have this pillbox that the bottom surface is now inside the conducting material. So what is the E at the bottom surface? 0. Yes, thank you for all of those who put in their answers and contribute. It's actually 0. And that gives me charge enclosed. I have the sigma times A, surface density times area. So I calculate E outside is what? Sigma over epsilon naught. Okay. Now notice this is different from a insulator. Do you guys still remember the result for an insulating sheet?
It should be over 2 epsilon naught.
Yes, for insulating sheet, because we have drawn E here. At the bottom, E is here. So you have E times A, top and bottom. So 2 EA is sigma over epsilon naught. So you get E is sigma over 2 epsilon, which is different from a conductor. Okay, so the answer is A. Reason for that is we're dealing with a conducting surface rather than an insulating surface, and that's different. Okay. There's another way to show that E parallel is 0, which is similar to what the approach I've done here. So I'm going to show that real quick here. So let's say I have this conducting surface. I'm going to draw a loop in this direction, L and H. So if I consider the E dot into DL along this loop with a very tiny width of the loop, then E dot into DL is a four line integration adding up, right? So the E will be E inside the conductor times L plus these tiny legs. It's almost 0. E inside is 0. The only contribution would be if there was non-zero E outside times L. So they have to be 0 because for electrostatics, this is always 0, right? Because curl E is always 0. Remind that's something we know. So this integration should be 0. So that means E parallel component, if you have an E outside that's parallel to the surface in the same direction as my L, must be 0 as well. So that's another way to show that you should never have a parallel component along the surface of your conductors, because if you do, the electrons are going to feel the force and they're going to move. So if you have a non-zero E field, that must be perpendicular to the surface, like this. Okay. Let's continue to answer some questions. Okay, now we're dealing with digging a hole inside a conductor. So we have a neutral conductor, there's a hole in the middle. We put a positive point charge in the middle. Can we say anything? So now what happens? There's anything more interesting happening now? Can we find out the total charge on the outside surface of the copper sphere? If we're talking earlier, we talked about if you have an excess amount of charges, they're only going to live on the surface. So what is now on the inner surface? What is happening on the outer side of the surface? Okay. Right. So this question is asking about the outside, but you can think about the inside. We're going to discuss those two together when we come back. So again, let's have a discussion on this for a couple minutes. Someone asked to confirm E is 0 when parallel. My notes here is this is a parallel component of E. If there were a parallel component of E, then it will contribute to the line integration by E times the length L. But you can see all of them add to be 0. It turned out this parallel component has to be 0 as well. So if you, to start with the derivation, you assume you have a parallel component, but it turned out it is 0. So there will be no parallel component of E at the surface of the conductor. Okay, so this question, I'm gonna go ahead and break out. So make sure you take a screenshot before you leave. Yes, people come back, please put in your vote. Just a few more seconds. Okay, any last minute vote? All right, let's take a look at this together. I'm gonna end this. All right. We're in the agreement. Majority of you guys are in agreement for positive Q. Okay, so anybody would like to tell us how did they figure it out how much charge should be on the outer surface?
Well, I think I'm wrong, but I'm going to explain anyway, just for the sake of learning. So positive Q, how I like to think about it is that like charges attract. So all the electrons are going to move toward the inner surface of that hollow sphere, while all the protons are going to be repelled and spread out towards the outer surface of that hollow sphere.
Sorry, did you just say like charges attract?
Listen, out there. I did. I meant opposite.
Okay, you're exactly correct, Sebastian. You're not wrong. It's precisely for the reason that you said. The negative charges will try to be pulled as close as possible to the positive Q, and where is the closest they can get is on the inner surface, right? They cannot jump through the surface. That's the closest they can get. The positive charges, the protons, we can say for the sake of reasoning, we can pretend the positive charge is being pushed away. But you know, in real life, it's the electrons that are moving. It's not the protons that are moving. So, but the effect's the same. The lack of electrons make it positive charged. So you can, for the sake of arguing, we can say the positive charge is going to be pushed to as far as possible, as far away. So how far could it go? I can only go to the outer surface, cannot go any further, cannot jump out. So you have negative Q inside and positive Q outside. That's very good. That is correct. It's a correct intuition. But if we want to be able to convince people, oh, how come it's precisely negative Q and precisely positive Q on the outside? We can convince people by using Gauss's law. So let's try to do that. So let's say I'm going to draw a Gaussian surface, just some random location inside the conducting material, inside this donut shape. I'm going to draw a Gaussian surface. Okay, so if I apply Gauss's law, I would say the E dot into dA over the surface is charge enclosed over epsilon naught. So what is the E right here on this Gaussian surface?
0? No, negative.
It's again, it's inside conducting material. What is E inside a conductor always?
0.
0.
Always 0. So you can simply just say, okay, the left-hand side is always 0. So Q enclosed, you must enclose 0 charge. So what kind of charge you're enclosing? You enclose a positive Q in the middle. So you're enclosing whatever charge on the inner surface, and they have to add up to be 0. And the inner surface is going to be negative Q, right? So that way you can convince people mathematically it's going to be precisely negative Q that lives on the inner surface. Now, what's on the outer surface has to do with this thing being neutral overall. This is still a neutral conductor. So whatever is on the inner surface and whatever net charge is on the outer surface has to add up to be neutral because that's what's given, right? Now, if it's neutral, then the out surface has to be a positive Q. If the outside is not, if the conductor is not neutral, but let's pretend that the conductor gets, the copper sphere has a positive Q on it. Okay, so what is the charge on the out surface now? Is it still positive little Q? If this thing is not neutral, if this thing has an excess amount of positive Q on it, So what happens inside? Do you think the inside is still negative Q? If we repeat the Gauss's law process inside the donut shape, we still
I
get,
want to say yes.
yes, we do. You're right, inside still negative Q. Yes, thank you. So the outside would have been whatever on the outside has to be plus the inside has to be positive Q. That's the total amount of charges this conductor carry. If the inside is negative Q, then the outside now has to be capital Q plus little extra little q. So it's going to be now positive Q plus positive little q. So just to make sure it's overall still going to be positive Q, that is whatever is given to you, depending on the question, right? Is as if this is 10 microcoulombs, and you're going to have negative 10 microcoulomb on the outside, on the inside. And if this thing is 30 microcoulombs overall, then the outside has to be 40 microcoulombs. Okay. You can see follows these steps. One is Gauss's law for the first step to get your inner and the overall charge about the conductor that give you the outer surface. So correct answer is C. Now let's move this charge to the outside. Okay, what happens now? We take it outside. What happens to the charge density on the inner wall? Okay, again, I'll let you discuss this for a couple minutes.
Dr. Ryan?
Yes. You need a room?
Yeah, was in room 10, but my laptop died. Sorry.
Yeah, no problem. Okay. Okay, I'm pretty much have everybody's vote. Any last minute vote now? All right, let's take a look. Going to end this. This is our results. Okay. Kind of split between B and C. So the majority of you think it's non-zero, but whether it has a zero total net charge on the inner or not. Okay. So for the, if we think that's non-zero, what do you think that the charge will be distributed? What it will look like on the inner surface?
Q negative or minus Q.
Would it be, where would it live on the inner surface? Like the left to the right or where?
It would be distributed all along the circumference of that inner surface.
So it's just the same as before, like this?
I'm so sorry. It's positive. It's Q positive. I think I may be wrong.
So like positive like this?
Yes.
And why would that be positive?
Well, if the same rationale as last time, you know, it's neutral before we bring the charge in, then we bring it in. So all of your electrons are going to be attracted to that positive charge, which is going to be distributed amongst the outer surface of that hollow sphere.
Ah, I see. So the negative charges want to flow as close to positive Q as possible. However, you can see here and here are two different distances. Here, I would say, yeah, it gets as close as possible.
Yeah, I was thinking it was going to be half and half.
Ah, okay, so we have a different answer now. We think half and half in the sense negative tried to be here and positive tried to collect over here.
No, the other way. We're positive on the right, negative on the left, because on the outside, you would get negative charges on the right. So then on the inside on the right, you would get positive, and then negative on the left, on the inside. If that makes sense. Yeah.
But wouldn't I argue yes? However, these are still closer than these. Even if it's inside, it's still at a closer distance to positive Q than these negatives.
I have a question. On the inside, wouldn't it all be positive, but there'll be more positive toward the left, a higher density of charge toward the left than the right?
Okay, we have another idea. Let's try to draw it. Something like that.
No,
not
like a gradient of positive on the inside where most of the positives are on the left or the right, and a little bit on the left.
Positives are here. More
So,
on the right hand side.
Like on the pre-flight question, I had like more positive charges on the right side, and then it would taper off to the left, less charges on the left.
Oh, okay, like that. Something like this.
Yes.
Okay.
Yeah.
And the negatives on the inner surface, on the outer surface.
Yes.
And
Yeah, almost split up the same way.
Yeah.
Okay, so similar kind of gradient, more closely here and then taper off here.
Yeah.
Okay,
That's what I was thinking.
I still argue these positive charges are still closer to these negative charges. Okay, let me present. I'm going to keep this in here. I'm going to present one situation. Someone suggests that that they think might be the case. So let's say I draw something like this. Oops, where is it? Lost myself. Okay, I'm going to pretend that I think, okay, positive Q will polarize the inner. So I think positive get pushed over here, negative get pushed over here. So I think inside I have some kind of electric fields this way, right? If I pretend that it's like this, then let me say, okay, let me draw sort of a line integration to a loop. Let's do a loop integral like around this path. right? So this loop integral is going to be whatever non-zero E you have inside. But actually, you can use this method for your charge distribution as well. Whatever is non-zero on the inside along the path, inside the material is E0. We know that already. So it's not going to be any contribution along the circle. So that's going to be some non-zero number, right? Some non-zero number. But E dot in dl is always 0 for static E field. So you have this dilemma. And then I argue that E has to be 0 inside the hollow sphere. And I should have no charge density inside. Because no matter what kind of charge density you have, you're going to have a non-zero E. Because if your E is 0 here, you're not going to have any charge density. We can do the same argument over this. Whatever kind of charge distribution you have, you're going to have some non-zero E field inside. Although I don't really know how to draw the E field, but whichever direction, this is more like more on the positive side, so it's more like toward the left, right? Because more charges on the right. Then you can do the same kind of path integral, and you argue it's confused, it's conflicting. The E dot dl is 0. So the answer, if you cannot draw the charges anywhere, maybe the answer is there are not going to be any charges inside. Not going to be any charges living on the inside of the surface, actually. So nothing inside. They will be positive, negative charges are going to live on the outside. Because that's what charges want to do. Normally, if you simply give a metal conductor some excess amount of charges, they will try to live only on the surface. And here, they will, so this outer surface is the surface they want to redistribute themselves. If you don't have a charge in the middle, then the charges have no reason to go to the inner surface. They only want to live on the outer surface because they want to try to get away from each other as much as possible if the excess amount of charge is positive or if all of them are negative. The only thing that changes by putting a positive Q here, it's going to draw some negative to this side and push some positive to the other side. It's going to be like this. Overall, it is still neutral. But nothing is happening inside, okay? And precisely because nothing is happening inside, the inside is sort of being shielded. Wouldn't you say that? It's been shielded by the metal from the influence of this charge outside. And what do we call this?
A Faraday's cage.
Yes, it's a Faraday's cage. So let's take a look at a Faraday's cage. So under the electric field of the Van de Graaff generator, you can see these tin foils will reflect. And now we're gonna put it in the cage. The outside is still the field, but nothing happening inside, right? The person is shielded by the metal cage. So this is Faraday's cage, right? If you have a hollow conductor and if inside is there's no charge inside, then the hollow conductor has a 0 E field inside. So you can have, what we have established is, okay, you can have a metal conductor, E is 0 inside. Now if you dug a hole in the middle, the metal, you dug a hole, which means you have removed a chunk of charge, sort of a chunk of material, As long as you're removing a total net amount of neutral material, then it's still going to be neutral. Nothing happens to the inside. This will become, this will have charges only if you put a little charge inside, then the E inside will be non-zero. But if you don't put any charges in the middle, the E will continue to be zero inside. Okay? Regardless of what's happening outside. Inside is always shielded from the influence of outside. Okay, so this question is zero everywhere. Now I'm gonna make things a little bit more complicated by putting both a charge inside and outside. Okay, so let's put both of them. And even more, this hollow sphere is no longer neutral. It has a net charge of positive Q. It's in a static equilibrium situation. And what is the magnetic field at a distance r away from the center? What is the E field right here? What would that look like? Okay. We'll let you discuss this for a couple of minutes. Okay, someone asked me to explain something. Can you be a little more specific? Which question do you want me to explain? Which part? Is it, oh, the Faraday's cage? The Faraday's cage is sort of just an effect, right, of what's going on. For this question, this one serves as if it's a Faraday's cage that the E field inside the hollow area is zero. Because I have sort of worked out, and one way to look at this is if you don't have E field in is zero, it must be pointing in some direction, right? Must be pointing in some random direction. And then you can do the E dot into dl along this path, and you get a E dot into dl non-zero, which is violating the no curl for the static field, right? So E must be zero inside. Another way to look at this, why the hollow area is zero, is as if you simply, okay, E zero here throughout. Now the only difference it makes, you dug a hole in the middle, you removed a piece of material, but you remove the total amount of zero charges. You shouldn't have changed the E field, right? So E should still be zero inside the hollow area. And also there are other ways to look at this. You see how people try to put different charges in there, and no matter where you put, it doesn't work. No matter where you put on the inside, it violates the charges the positive want to get further and negative want to get closer. None of these ways works. The only way for this to work is there's no charges on the inner surface. Okay. All right, thank you so much for asking. And let's look at this question, okay? What does the E looks like at the distance r away from the center? Now you have both inside and outside. One more second. Okay, all right, let's take a look. All right, so a lot of you voted that it looks just like the Coulomb potential, right, due to a point charge. So would you, anybody would like to tell us what physics approach do we use to get this answer? What did you use in order to get a KQ over R squared?
Thinking about it like Faraday's cage, if the inside is shielded from the outside, and we're only talking about an E field at a distance r from Q that's inside of the hole, any Gaussian surface that you're going to use is going to be inside the hole. So one, you can just ignore what's happening on the outside because of Faraday's cage, and you're not including any charge that's like inside the surface. So you can sort of just think about the inside as the only thing that's happening. And so you can just use E equals KQ over R squared.
That's very good. In this case, we use the Gauss's law. We're giving the spherical symmetry. So whatever is inside, you don't have to think about the influence of this little positive Q on the outside. So it's simply just going to be E dot into dA over Q enclosed. In this case, is a Q prime over epsilon. So you're going to get choice A, which is correct. Now, we're going to move this to be just a little bit more complicated. We're not going to be able to solve this, so, but I want to, and also we're not going to have time to vote, but I want to talk through this question. But now imagine I move this positive Q away from the center. Let's shift it off center now. And now I'm asking, what does the E look like in this region? It's still going to be Coulomb-like, or is it going to be complicated? I don't have time to vote, but I will let you know that it's not going to be Coulomb-like. By shifting it away from the center, make it really hard to calculate. But if it were Coulomb-like, you can imagine Coulomb potential is this, right? It's going to be perpendicular. It's just going to be directly away from the center. And that's not going to be okay, because you can see if your E field is Coulomb potential, so in the radial direction from your positive Q, then you can see that it's not perpendicular to the surface of the conductor. And we had just talked about your E field lines has always to be perpendicular to the conducting surface. So a Coulomb potential will not be able to allow that. It's going to be complicated, and it's going to be hard to calculate. So for off center, what it will look like is that you will attract negative charges to the middle. So, okay, so let me go back to this one. When it's on center, let's think about the charge distribution. You're going to have negative charges be attracted by the positive in the middle. So the inner surface is going to be negatively charged. And the outside is going to be positively charged. However, because you have this little Q here, it's going to push the positive away. So what end up being is that it be more positively charged on the left-hand side and less positively charged on the right-hand side. But overall, it's still to be positively charged on the outer surface. So this is what it looks like. But if I move things away from the center, what's happening now is the inside is still negatively charged, but it's not going to be uniform anymore. So I'm going to have more negatives to the right-hand side than the left-hand side, because I have my charge generate a stronger field on the right-hand side that is closer to the surface. So more negatives on the right-hand side, less negatives on the left-hand side, and the outside so let me get rid of this charge. I'm going to say, just think about something off center here. And don't think about anything else. I'm going to throw this away from the picture. Okay. So what's going to happen right now is this will be negatively charged and non-uniform, and this is a little bit less dense. And anybody would like to predict what's happening on the outside? Nothing. There is no positive Q here. So just this situation. What is on the outside? The outside is positively charged, right? Do you think the outside positive charges are uniformly distributed? Or is it non-uniformly distributed? We know it's uniformly distributed when it's on center. Both inside and outside are uniformly distributed. But now I move this off center. Now I claim only the negative inside are going to be non-uniform distributed. Outside is still going to be uniform, because you can see that whatever E field that generated by these negative charges and the positive charges already canceled out. E is 0 inside the conducting materials. Okay, the positive charges are not going to be affected. This is sort of an idea is you try to hide the charge in the middle. You cannot hide it because you can pick up the E field due to a positive Q outside. You know that there is a positive Q here. You cannot hide this charge. But you have lost information about where it is. You don't know exactly where this charge is. Is it off center? Is it on center? You don't know. Okay, so and this is sort of a simplified version of this question. This question, by putting a positive Q here, of course, you're going to make the outside to be non-uniform as well. But before we can even think about that, I drafted this question to see what it will look like without the positive Q. This one, okay, the pre-flight, I don't have time to go through them very in much detail. So I'm going to go through them one by one real quick and I post solutions, okay? This one, this is wrong because the positive charges on the outside should be uniformly distributed. There's no reason for the positive to be done. B, it is possible. If your Q inside is negative and your this one is positively charged, then these positives will have to live on the inner surface. C is wrong. These positive and negative should be uniformly distributed. D is wrong because there's no charge in the middle. There's no reason for these positive charges to live on the inner surface. Now E is correct. F is wrong. The positive should be uniform in the middle. The negative is okay, it's non-uniform inside. G, the negative charges is non-uniform. It should not be uniform like this one. You can see it's just a variation on the question we have just posted in the clicker. So if you go through the clicker and make very careful to understand the clicker questions, these would be easier to figure out, okay? All right, sorry I went over a little bit. If you have any more questions, feel free to shoot me an email. I know conductors can be very confusing. If you want to discuss offline, then I'm happy to talk about it. All right, I'll see you guys on Wednesday. Bye, everybody.
Thank you, Dr. Ryan. Have a nice day.
You too.
Dr. Ryan, I have a quick question.
Yeah, go ahead.
Thank you.
Is there a site online where we could work with these simulations?
Yes, there is. Send me email, okay, and I'll find out.
Okay. Okay, thank you.
Can you post it in the Discord once you have it?
Yes, of course.
Thank you.
You're welcome.
All right.